Okay, welcome everyone to the second video for this week, where we're going to discuss derivatives of exponentials, namely the derivative of a very special exponential function called the natural exponential, excuse me. And it's a little weird how you arrive at this exponential function, so I'll try to motivate it in some way, and I hope this is helpful. It may or may not work, may or may not be, but just bear with me and humor me for a moment. So in the last video, oops, sorry. We introduced exponential functions. So these were functions of the form f of x is equal to a to the x for a positive number. And you really shouldn't have a be equal to 1. If a is equal to 1, you're just multiplying 1 by itself arbitrary times. It's a constant function 1. And I said, like, you can think of this, if x is a positive integer, this a to the x is computed by multiplying out a by itself x times. So a to the 5 is a times a times a times a times a, and so forth. If a is a negative integer, we do that same thing in the denominator. It's 1 over a to the x. And if a is rational, it's involving a power of a root and so forth. So this is not, but this is a function. These functions I kind of explained at the very beginning of the first video are important for applications and thinking about bacterial growth, spread of a virus. They're important in finance, but we need a little bit more theory or a little bit more background to talk about that. They appear everywhere. So from a calculus perspective, and a deep reason why they appear in all these weird places is that their derivatives have a very, very special property. The derivative of an exponential function is proportional to the function itself. And this is the only type of function that has this property. So I'll write this out and explain what I mean by this. So one reason why exponential functions are so important in applications and in calculus in general is that the derivative of an exponential function is proportional to the function itself. Okay, so what does that mean? What does that mean? So i.e., let me just clean this up a bit. If f of x is equal to a to the x, then f prime at x, the derivative, is equal to some constant c times a to the x. So it's equal to c times f at x for some constant c, which depends on the base a, which in general depends on the base a. Okay, so again, this may not be, maybe for you at this stage, it seems like a big do about nothing. I mean, who cares if the derivative is of a function is a multiple, is proportional to the function itself? But we'll see when we study interest, and if you go on and study more complicated things in finance, that this is actually really, really an important condition. Like that this kind of condition arises very, very naturally in life and in applications. Unfortunately, my experience in business is rather limited, but one example I am aware of, very kind of top of my head, is if you're modeling like air resistance, for example. So in the, you know, we talked about, we did some silly physics problems back, you know, earlier on, and, you know, we were talking about, you know, some say some object falling under gravity, but you might have a force of gravity if you drop an object from a cliff, say into the sea, right? You might have a force that, you know, you have a force of gravity acting down on the object, but in real life, there's also like a wind force acting, you know, wind resistance acting in the opposite direction. And it turns out like this is a much more, we didn't talk about wind resistance because this is a much more complicated problem if you have it in the picture. But what the force of the wind is proportional to the velocity of the object, which kind of makes sense, right? The faster something's traveling, the more wind resistance it will undergo. And then if we remember that force is essentially like mass times acceleration, you end up with a situation where like the derivative of velocity is proportional to the velocity in terms of like the effect of the acceleration due to the wind resistance. And so because this naturally comes up in this problem, and exponential functions have this property, right, that their derivative is proportional to the function, the solution to the motion involves an exponential function. So that's an example where exponential functions arise naturally in nature out of this process that the rate of change of the velocity is proportional to the velocity for wind resistance. And again, when we will do compound interest in finance, and we'll talk more about that. Similar type of thing occurs, and we'll have to use exponential functions there as well. But that takes a little more explanation. Anyhow, just some motivation. So we have exponential functions have this property. So I'm not explaining where it comes from. It's just a fact right now. So we want to study, so the natural exponential function, I should kind of do both of these things here. So the easiest exponential function to understand is when this constant of proportionality C is exactly 1, right? So, and that's called the natural exponential function. So the natural exponential function f of x is the unique function for which f prime at x is exactly f at x, i.e. the constant c above here, the constant c is 1. Okay, so this exponential function, however, is a bit funny looking, and so we just have to get used to the fact that it's a little funny looking. So in this case, f at x is equal to e to the x. Okay, now what is this little e? So i.e. the base a is a number denoted by e, by lowercase e. Okay, where e to the e is called Euler's number because it's discovered by a Swiss mathematician, Euler. It is an irrational number. So this is a weird number. Which is approximately equal to 2.7581. Okay, non-terminating decimal exponent is an irrational number, almost 3, but not quite. So it's like 2 3/4-ish, roughly. Okay, and so it's just a really weird number. You see the plot on your calculator. Euler discovered this when he was studying calculus in the very, very early days, and this kind of issue about when is the derivative of a function equal to itself. And so, so the function e to the x, f of x equals e to the x, is called the natural exponential function. And it has the wonderful property that the derivative of e to the x is e to the x. Okay, so that it is its own derivative, right? So i.e. f prime of x is f of x. Okay, so again, why this all works out this way is kind of a mystery. Euler discovered this. We'll leave it at that for now. But it's because of this property with the derivative, that the derivative is itself. I mean, this function appears in so many different places. In applications, it is too much to mention. Okay, so let's do some examples with differentiating e to the x. So I'm gonna, like I said, I'm kind of following these type notes, section 4.2, and you can see it in the computer. It's probably a little tricky. They're up on Canvas, following them kind of loosely. I'm not going to go into what the graph is right now of e to the x or its close relatives. The graphs do not come up on this week's homework at all, so I'm not quite sure why they're here. They are important. We'll talk about them later. But for now, I want to kind of get started on practicing differentiating this creature and its and expressions and other functions constructed from e to the x. There's an example about solving an exponential equation involving e to the x. I'll leave that to the live meetings or the homework. We did one in quite a lot of detail last time, so in the last video. So examples of differentiating e to the x. The natural exponential and friends. Okay, so closely related creatures that we can get out of the exponential. So first example. Differentiate the following function. Y equals x squared plus x plus 1 times our friend e to the x. Okay, now this type of thing is maybe a little tricky because it's combining something new with something old. So to be able to tackle this problem, we need to take a bit of a trip down memory lane. So first, we need to recognize that y is the product of two functions, f of x equals x squared plus x plus 1, and our newfound friend, our new favorite function, g of x equals e to the x, right? So y is the product of these two guys. And recall, we have a rule for differentiating a product of two functions. Don't think it's come up in a while, so it's good to review it. And recall, we can use the product rule to find y prime, right? So y prime equals f prime at x, the derivative of the first guy times the second factor plus the first factor times the derivative of the second. All right. And so we guys gotta compute these derivatives in the case of for this f and this g, and then just plug them in to the formula. Plug them into the formula for the product rule. So y prime equals derivative of f. Okay, maybe we should write them out first, so don't get ahead of myself. So we have that the derivative of f, this is just an easy power rule problem, so this is just 2x plus 1. And the derivative of g, what I was saying before, this is as easy as it gets. The derivative of g is just g itself, it's just e to the x. The derivative of e to the x is e to the x. You know, it just, like as I said, it's my favorite part of calculus. It doesn't get any better than that. There is no real rule to be had. Okay, and so let's use that in the formula for the product rule. And so y prime is equal to 2x plus 1 times e to the x, so times g to x, plus f, which is x squared plus x plus 1, times e to the x. The derivative of g is just g itself. Doesn't get any better than that, folks. And we could simplify this a bit. I guess I shouldn't be like super duper lazy. So we could factor out an e to the x. And then we get 2x plus 1 plus x squared plus x plus 1. So we get that y prime is e to the x times x squared plus 3x plus 2. All right, so just combining like terms in here, you got 1x squared, you got 2x, you got an x, you got 3x, 1 and 1 gives you 2. So not so bad, right? Okay, so let's make it a little bit more interesting maybe. So we can also combine our new formula for the derivative of y equals e to the x with the chain rule. And perhaps this is where things get a little bit more interesting for us. And again, this does come up a lot in applications. So I'm going to do an example from the homework now, and you can see how this works. So you can do the homework. So differentiate the following function. So it's y equals the square root of e to the x plus 5. So e to the x plus 5 all under the square root, okay? Okay, so to do this, to differentiate this guy, we have to recognize that this function is the composition of the function e to the x plus 5 with taking the square root. And then we have to remember the chain rule. So all that hard work we did about the chain rule was partially so we could deal with differentiating compositions involving things that aren't just polynomials. Like so far what we've done with the chain rule is to take powers of other functions. Now we're going to be taking powers of polynomials, sorry. Now we're going to be taking powers of exponential things and exponentials of other functions. So all that kind of crazy hard stuff we do with the chain rule is really going to come in very useful here for these type of examples in this section. So to differentiate this, function, we need to recognize it as a composition of y equals f at g at x, where the outermost function, where f at x is the last thing you do to compute this function, which is take the square root, right? So if the last button, if you were computing this quantity, e to the x, the square root of e to the x plus 5 on your calculator, the last button you'd hit is take the square root. Right? You'd first figure out what e to the 2 plus 5 is, say, on your calc, and then you would hit the square root. So the outermost operation, right, is take the square root. Remember the chain rule, we peel the onion layer by layer, working from the outside of the onion into the center of the onion. I don't know if it's called the core of the onion, heart of the onion. I don't know. I eat a lot of onions, so I should know that. And the innermost function is the first thing you do. Sorry, is e to the x. The plus 5 is not in the exponent. It's just e to the x plus 5. Okay, and then we recall that the chain rule says that the derivative of the composition is the derivative of the outer evaluated at the inner times the derivative of the inner. Okay? So let me write out this again, because it's kind of disappeared up. We have all the pieces here, but the actual function disappeared into the sky in the notes. So we had y as the square root of e to the x plus 5. So I'll write this as e to the x plus 5 to the 1/2. Okay, because taking the square root is 1/2 power. So derivative is derivative of outer, so it's the derivative of taking the square root, which is a power function. So the half comes down. I'll just put parentheses here because we're going to have to plug in the inner function, right? So derivative of outer at the inner. So derivative of taking the square root is half stuff to the minus 1/2. The inner stuff is e to the x plus 5, and then times the derivative of the inner function. So that's the chain rule. So by chain rule. So I can now compute the derivative of the inner function, this guy here, right? I mean, this is just the sum rule. So let me just write it out. So it's the derivative, it's 1/2 e to the x plus 5 to the minus 1/2. Then I get times the derivative of e to the x plus the derivative of 5, right? The derivative of 5 is 0. That's just a constant. And the derivative of e to the x is e to the x. That's what makes e to the x so special. So since the derivative of e to the x is e to the x, we have that the derivative of y is 1/2 e to the x plus 5 to the minus 1/2 times e to the x. And I guess if we wanted to be fancy, we could put the negative exponent in the denominator. Again, this is not 100% necessary, but this is e to the x in the numerator, and then 2 times the square root of e x plus 5 in the denominator. Okay. So I hope this can remember the chain rule a bit, because we're going to keep pushing on with it, and maybe hopefully this isn't too bad. But I think these questions are kind of fun. Okay, so the next bit, if we start, we're going to start 4.3 a bit. So in this problem, this little exercise, right? Where did it go? There it is. Right. So in this case, we had the square root of e to the x plus 5. Being a little slow, right? So we have the square root of e to the x plus 5 here. And there's a composition of the two functions, f and g. The outer function was the root, and the inner function involved the exponential. So the outer function was take the square root, inner function involves exponential. Now I want to do differentiate compositions of functions where the roles are reversed. So in other words, the outer function will be the exponential and the inner function will be some kind of polynomial or something involving, you know, algebra, some kind of algebraic functions, the kind of functions we've been differentiating up until now. Okay, so that's what we start with in section 4.3. I mean, it's the same thing, but in a different order. So this is section 4.3. So now I want to differentiate functions of the form y equals e to the g at x. So this is a function of the form f at g at x, a composition of functions where the f at x is e to the x. So the outermost thing you're doing is applying the natural exponential function. So you're exponentiating this function g of x, okay? Now, chain rule gives us a very nice way to handle the derivatives of this. And again, because the derivative of e to the x is so easy, this becomes a very straightforward thing to do. Now we can compute, y prime in a similar, using the chain rule in a similar way to the above, as we did above. In the last example. So y prime is the derivative of the outer at the inner times the derivative of the inner, right? But the derivative of the outer guy of e to the x is just e to the x. So the formula we have here as a derivative is e at g at x, right? This is the same thing as this, right? Times the derivative of the inner, whatever that may be. So that's the general formula. So summarizing, if we have y equals the exponential of a function g at x, then the derivative is just that function again, e to the gx times the derivative of the function you exponentiated. So if you want to memorize formulas, by all means, go ahead. But it's a very, very straightforward calculation with a chain rule, just remembering that the derivative of the exponential is itself. Okay, examples. Okay. Let me go to the next page. I can go here. Start here. Differentiate the following function. So f at x equals e to the square root x of x squared plus 1, right? So now it's kind of like a little bit like I was saying, the reverse of the last example. Now we're taking e to the square root rather than a square root of something involving e. Okay, so this function is of the form f at x equals e to the gx, where g at x is the square root of x squared plus 1. So f prime at x is e to the gx times the derivative of g prime at x. So let's write that out. So f prime at x is equal to e to the square root of x squared plus 1 times the derivative of the square root of x squared plus 1. Now, this is actually a difficult question if you think about it, because this, or it's a little more, more complicated than we've done lately, because now the derivative of g also involves a chain rule, right? So this is actually a question that involves use of the chain rule twice. We use the chain rule once to get this step, as I explained above. Now, this derivative also involves the chain rule. So note, the derivative of the square root of x squared plus 1 also requires the chain rule. Right? This ddx, the square root of x squared plus 1, is the composition of, say, a function f and h at x, where the outermost function f at x is the square root of x, and h at x is x squared plus 1. So it's kind of like a little bit what we were doing in the last example, except now the inner function is just a polynomial rather than something involving the exponential. And so, using the chain rule again, we obtain. So let me kind of see and keep that on the screen. F prime at x is e to the square root of x squared plus 1 times 1/2 to the minus 1/2, that's derivative of the root function, right? Evaluated at the inner, x squared plus 1 times the derivative of the inner, so the derivative of x squared plus 1. Clean this up a bit so you can see it a bit better. So that's the derivative of the inner, and that's the derivative of x squared plus 1 is just 2x. So f prime at x is e to the x squared plus 1 square root times 1/2 x squared plus 1 to the minus 1/2 times 2x. We can cancel, notice that we can cancel the 2 here with the 1/2. And you can make this a little nicer if you put the negative exponent in the denominator. It will look a little less hideous. So I'll write it this way, is x times e to the square root of x squared plus 1 divided by the square root of x squared plus 1. Okay, so that's using the chain rule with the exponential the other way. So we should probably do a few more examples. I'm just going to pause for a second to get some more water. Okay, so now I want to do an example. I'm going to do one from the homework because the numbers are a bit better, of finding a max and min and using the techniques we learned, like second derivative tests, to determine whether a point is a max or a min for a function that involves an exponential. Things get a little bit, I don't want to say terrible, I don't get terrible, but they get a little more tricky here because you have to learn how to manipulate, you have to be comfortable with manipulating algebraic expressions with exponentials, which can be a little bit more complicated than just dealing with polynomials like we've done before. So finding relative max or min for exponential functions. Okay, so there's a few things to be aware of. Okay, so first, before I do an example, note that e to the x, e to the x is positive for all values of x. Remember, this number e is like 2.7581, whatever, it keeps going in a crazy way, is some positive number, irrational, but positive number, and you're just taking powers of that number. So it's always going to be positive. You're never going to get 0, and you're never going to get a negative number that way. That's very important to keep in mind when you're dealing with evaluating e to the x at different points, and especially in the second derivative. Okay? Second derivative test. So keep this in mind, and then I want to do an example of finding the relative max or min. So here's an example. And it's going to be from the homework. So find the value of x at which the function, the following function, has a possible relative min or max, and then use the second derivative to determine the nature of the function at this point. So, I mean, I'll just put it this way. Use the second derivative test to determine whether the point is a max or min. Okay, so what's the function? So the function that tells us to work with is f at x equals 6x minus 2 times e to the 6 minus 3x. Okay, so it's a little more complicated than what we've been dealing with in the past. Okay, so remember the procedure. This procedure for finding the max and min is still the same. It's the same procedure we've talked about for weeks now, right? So if I just put this in parentheses, right? So procedure for finding the max or the min is the same as it's always been. Right, you look at f prime at x, you find f prime at x, then you find the points x for which f prime at x is 0, right? You solve that equation, and then find f double prime at x, the second derivative, and check whether it is positive or negative at these points. If it's, sorry. So it's the same deal as before. Now we just have to, the derivative will be a little bit more complicated because we have to, we have to deal with exponential functions now. It won't be the same formula for the derivative we've been dealing with in these problems previously, but it's not going to be much, worse. The procedure is the same. Okay, so we start with, okay, so I'm going to start with, damn, it goes on to the eraser, copy this puppy. So we start with this guy, and you recognize that this is a product of f with this function g. So this, I mean, the derivative is going to be a bit complicated. That's the one big difference with what we've been doing before, because we're going to have to use a product rule to unravel this at the first step. And then the derivative of g is going to involve this new rule I was telling you about, where the derivative of an exponential of a function, which is a chain rule application, but it's a relatively easy chain rule. Oh, sorry, I shouldn't have used the letter F because it's already used here, so I should have called this like, maybe better to have called it G, the product of G and H. Okay, so to compute f prime at x we have to first apply the product rule. So you get f prime at x is equal to the derivative of the first factor, so the derivative of 6x minus 2, right? Times the second factor plus the second factor times the derivative, sorry, plus the first factor times the derivative of the second factor. Okay, so now we can unravel this a little bit more, right? So the derivative of 6x minus 2 is easy. That's just, by the power rule, that's just 6. So it's 6 times e to the 6 minus 3x plus 6x minus 2 times the derivative of this puppy. So the derivative of e to the 6 minus 3x. And now for this guy here, we use this rule that we just learned, right? So to compute the derivative of e to the 6 minus 3x, we use the rule we use the rule ddx of e to the g at x is equal to e to the g at x times g prime at x. Okay, so that rule for differentiating the exponential of a function g at x, which we got with the chain rule. So using this rule, we have that f prime at x is equal to 6 times e to the 6 minus 3x plus 6 minus 2, okay, times, what's the g at x? Here, it's just this function 6 minus 3x, okay? So it's a linear function, so that's really easy. So times e to the g at x back, so e to the 6 minus 3x times the derivative of 6 minus 3x. The derivative of g, right, is just the derivative of 6 minus 3x. Okay, so we can just do one more derivative and we're done. So f prime at x is 6 e to the 6 minus 3x plus 6 minus 2 times e to the 6 minus 3x times the derivative of 6 minus 3x, which is just minus 3. Okay, now we can clean this up a bit. What's the best way to clean this up? So f prime at x is equal to 6 e to the 6 minus 3x. I'll say minus or plus minus 18x plus 6 e to the 6 minus 3x. And now, because we're going to have to solve an equation, we should kind of factor out the exponential factor. So you get e to the 6 minus 3x, 6 minus 18x plus 6, and f prime at x is e to the 6 minus 3x minus 18x plus 12. Okay, whew, that's as simple as it gets. Now, let me just make sure this is clear. So this is this is a minus 18 here, right? I took a minus 3 and I multiplied it inside here. So I get minus 3 times 6 is minus 18, and then minus 3 times minus 2 is positive 6. Now, what I did here is I factored this exponential out of both terms. Now, the reason to do that I did this, not just because it looks nice, is because it makes it much easier to solve the equation f prime at x equals 0. Okay, so that's what we need to do now. So now we need to solve the equation f prime at x equals 0. So 0 equals e to the 6 minus 3x times minus 18x plus 12. And now you remember hopefully what I was saying at the beginning of this example, that this thing here, this e to the anything, is never equal to 0. Can never be equal to 0. So you can divide both sides of the equation by this term. And that's what allows you to actually solve this. So since e to the 6 minus 3x is never 0 for any x, we can cancel it from the equation. To get this simple equation, zero equals minus 18x plus 12. Now we can just solve this. So we get 18x equals 12. So x equals 18 over 12, which is 3/2. So that's the point where f prime at x equals 0. So I'll drink to that. Some nice water. Okay, so this was, again, like maybe a bit more involved of a calculation than we had to do in the previous weeks, because, you know, we had to use product rule with chain rule to get to this derivative. And then we had to do some kind of maybe non-trivial factoring, right, to be able to simplify the derivative so that we could solve this equation. And then the key step was that this guy, this exponential term, is never 0. So we can cancel it from the equation and get a very easy linear equation that we can solve using old school techniques back from when we were kids. Okay, so now we need to check. We're not done yet, right? Because the question asks, is this point a relative maximum or relative minimum? We got to use the second derivative test now to check that. So now we need to use the second derivative test. To check if the point x equals 3/2, is a relative minimum or maximum. So I need to compute the second derivative first. So let me go grab the first derivative. And you should use, probably easiest to use, the most simplified form of first derivative, which is this fellow. And I could even simplify it further, I guess. Okay, so the first derivative was and actually, I mean, I don't know. Well, we'll leave it like this. I could factor out. I could factor out a 6 from inside this factor, but that's not going to do much good for us. So f double prime at x is the derivative of this guy Oh, sorry, guys. I just realized I made a bit of a boo-boo. It's 12 over 18. A little bit dyslexic there. So it's 2/3. Sorry about that. Sometimes things can get flipped in my head. So it's 12 over 18 or it's 2/3. Okay, so hopefully that's not, you can fix that in your notes. All right, so now go to the second derivative. So this is derivative of this guy. And this is, again, a product rule, chain rule combination. I'll go through it a little bit faster because it's kind of a repeat of the same calculation we just did with slightly different numbers involved. So the derivative of the first factor times the second plus the second, the first factor times the derivative of the second. And so this, again, using the chain rule, exponential rule, this works out to be e to the 6 minus 3x times minus 3. So that's the same thing we just did we did above in the first, in this calculation here. So that's exactly the same calculation we did way up here. Okay, so exactly the same thing. And then multiply it by this guy. And then the second guy, derivative of this is just minus 18. So f double prime at x is equal to e to the 6 minus 3x. And you get, so I'm factoring up this guy. So you get minus 3 times minus 18. So that is 54. So you get 54x plus 12 minus 18. And so f double prime at x equals e to the 6 minus 3x times 54x minus 6. Okay, so that's the second derivative. These calculations get a bit lengthy, but they're not terribly hard, but they're definitely much more involved than just dealing with polynomials. And now we plug in x equals 2/3. Right, okay, so f double prime at 2/3. So this is e to the 6 minus 3, 2/3 times 54 times 2/3 minus 6. And I mean, we can work out exactly what it is, but it should be pretty easy to see what the sign is. So this is e to the, if you want, this is e to the 4. And then 54 times 2/3. So 54 is, scratch work here, 6 times 9. 2/3. So this is 2. Yeah, so it's 18. 2 times, sorry. Yeah, so it's 2. 18. So it's 36. So this is 36 minus 6. So that's a little scratch work. And so this is e to the 4 times 30. So 30 e to the 4, which, remember, e to the 4 is always positive. So this is positive, and that's what's important. It's the sign. So you can kind of tell just from looking at this, right, that it's going to be positive. But if you really want to work it out, you got to do some kind of back of the napkin calculations here. Okay, so by the second derivative test, the graph is bending up at the point where it's 0. So by the second derivative test, it's a min. So x equals 2/3 is a relative min. Okay, so that was a long problem. That's the longest question on the homework. So you should be thankful I did it for you. Anyhow, let me just say there is one more type of problem I haven't covered. It's about valuation. They're very straightforward. You can give that a crack on the homework. If you're having trouble, I can do an example of it in the live meeting. It's much easier than this. So for now, I'll leave it off there for this week, and hope you have a good week. And I hope to see you in the live meeting. So let me just, there's another, make that correction here. This has to be 2/3, not 3/2. And off we go. All right, see you later. Thanks for tuning in.